Hi everyone. In this video lesson, we're going to learn about the cross product or vector product. Let's get started. So as a bit of motivation, we're going to do a little bit of extension of the dot product. In a lot of applications, it's going to be useful to be able to find some vector that's perpendicular to other vectors. So we're going to do this, and then actually today we are going to do look how to do this quicker, some kind of product. Anyway, let's get started here. So we're going to be finding a vector that's perpendicular to the vector u, 1, 5, minus 1, and the vector v, minus 3, 1, 2. In this case, I've said for us to be able to do this and get two equations, two unknowns, I said the z value has to be 1. The reason why will become more obvious in a little bit. But let's work through this. So recall the dot product gives us a way to show that two vectors are perpendicular, right? So if the vector I'm looking for, xy1, is perpendicular to u, oh, my boys unplugged my tablet. So let's just fix that up. The joys of having kids. There we go. So if xy1 is perpendicular to those vectors, it's yellow here, then xy1, that vector dotted with vector u, so dotted with 1, 5, minus 1, has to equal 0. We showed that in our lessons about the dot product. If we actually do that dot product, we get this. We get x plus 5y minus 1 equals 0, or x plus 5y equals 1. We have an equation with two unknowns. If we do the same thing with vector v, because whatever this vector is, it has to be perpendicular to v as well, we get minus 3, 1, 2, and that dot product has to be 0. We get another equation. We get negative 3x plus y plus 2 equals 0, or minus 3x plus y equals negative 2. So if we can solve that linear system, we'll have our vector. We'll have x, we'll have y. So there are lots of ways to solve a linear system like this. I might use substitution for this one, and then maybe elimination for the next one. But I can isolate the x in the first equation and sub it in the second equation. This creates an equation with only y in it. That means I can solve it. So distributive law, negative 3 plus 15y plus y equals negative 2. That will be 16y. Move the negative 3 over. Negative 2 plus 3 is 1, and I get y is 1 over 16. And now I can find x. X was 1 minus 5y. So that'll be 5/16. So 16 over 16 minus 5 over 16. X would be 11 over 16. So my vector that's perpendicular to both u and v is this. It is 11 over 16, 1 over 16, 1. And there we have it. We're going to do this one more time, and then I'm going to show you guys a quicker way to do this. So a very similar problem, but this time we're going to find a vector of the form. This time we're going to say that the y value have to be 1. So we're going to get a different vector, but the process will still be the same. So if you want to pause the video and try that on your own, you can. Or if you want to follow along with me too, you can do that as well. It's going to be the same process though. Our vector, whatever our vector is, x1z, dotted with u, which, just got to double check, was 1, 5, negative 1. has to equal 0. Gives us an equation. X plus 5 minus z equals 0. X minus z equals -5. There's our first equation. Also, x1z dotted with our second vector, which was -3, 1, 2, has to be 0. So -3x, that's +1 plus 2z equals 0, or -3x plus 2z equals -1. Call that equation 2. Here's what I might do for this one. Let's use elimination. I'm going to multiply equation 1 by 3 and write it down here. So I get 3x minus 3z equals -15. And that was equation 1 multiplied by 3. And now I can add these two together to eliminate the x's. And I get -z equals -16, or z equals 16. If we sub that into 1, we get x minus 16 equals -5. That would mean x is +11. And our vector here that's perpendicular to both is 11, 1, 16. Now, if you look at the relationship between these two answers, 11, 1, 16, and 11 over 16, 1 over 16, 1, maybe you can see a connection. If you recognize that those are scalar multiples of each other, then good for you. And in fact, that makes sense. Any vector that's perpendicular to these two guys, so if you imagine U and V span a plane. If you were to take linear combinations of U and V, you can kind of get anywhere you'd like on that plane I drew. Any vector perpendicular to both would have to be kind of pointing up from this plane, like a pen pointing out from your tabletop. And, there's lots of different vectors that are perpendicular to both U and V, but they'd all have to be along the same line. They'd all have to be collinear or parallel. And that's what we saw here. 11 over 16, 1 over 16, 1. If you scale that vector by 16, you do get 11, 1, 16. And that brings us to kind of our what we're getting into today. So using the dot product and some linear systems, we showed that any vector perpendicular to both vectors has the form 11 times some number, that number, and 16 times that number. That, which is just a fancy way of saying that any vector perpendicular to U and V was a scalar multiple of the vector 11, 1, 16. We give this vector a special name. We call this the cross product of U and V, or vector product. I'm going to move my picture up here. So given two vectors in R3, so the components of A, the components of B, I'm going to give you guys a formula to how to calculate A cross B. The derivation of this formula, it's kind of a generalized version of kind of the problem we did here. I've posted it online, but it's just kind of, it's a little bit beyond the scope of the course. You guys could understand the math, but it's just very, lots of variables floating around. So if you want to look at it, go ahead. But you guys can just start using it. But I actually want to get a visual first and just reinforce what we're talking about when we talk about the cross product. So I'm going to draw a plane here, and then just two generic vectors. Call that vector A, and we'll just say vector B. Vector B is pointing down here. And what the cross product gives you is a vector, so A cross B, that is perpendicular to both. And actually, this is really important. I am actually just going to switch the order of where my vectors A and B are. You'll see why in a bit. But if you copied it down the way I did originally, could you change it? Have A on the bottom, B on the top, like so. So how do we calculate this, given any two general vectors? How do we calculate this vector that's perpendicular to both, this cross product? Well, here's the formula. And as I said, the derivation will be on the on Brightspace. So I'm not going to go through the derivation right here. All right, so to get the x component, you kind of ignore, to get the x component of the cross product, you use the y and z components of the original two, like so. You do a2 times b3, and you subtract a3 times b2. And you do similar things for the y and z components of the cross product. For the y component of the cross product, we leave out the y components of each of the guys originally, a and b, and we do a3b1 minus a1b3. And then finally, we do a1b2 minus a2b1. If you would like, we can actually verify that this works with our two vectors. Let's actually just try it out. I think u was 1, 5, minus 1. So let's say we have 1, 5, minus 1. And let's say we have b. Let's make sure. Yeah, we can do this. I'm not going to be repeating myself later. Vector b was negative, let's say is negative 3, 1, 2. And let's just convince ourselves this formula works. All right, so a2 is 5, b3 is 2, minus negative 1, b2 is 1. And then we have negative 1 times negative 3 minus a1 is 1, b3 is 2, and then a1 is 1, b2 is 1, minus a2 is 5, and b3 is 2. Three. I think I did something wrong with the last one. A1, B2, A2, B1. 1 times 1, 5 times negative 3. There we go. 5 times negative 3. All right, let's just work this out. Oh yeah, we're good. 10, subtract negative 1, that's 11. 3 minus 2 is 1. And 1 subtract negative 15, that does give you 16. So sorry for the brain fart there. But yeah, the formula does check out. The formula can be a little cumbersome to memorize and use. So I'm going to show you guys maybe a visual tool that you can use instead. But that's the cross product formula. The vectors A, B, and A cross B form a right-hand system. So what this means is if you take your right hand, if your index finger is vector A and your middle finger is vector B, then your thumb will point in the direction of the cross product. In my diagram here, you can see that rule does check out. I kind of think of it this way. If you use your right hand and treat your right hand as vector A, and you curl your fingers towards vector B, your thumb points in the direction of the cross product. So I have vector A, vector A going this way, curling it towards B, my thumb's pointing up. Now that's a lot harder to talk with you about, not being with you, so we can all kind of use our right hands. But the way I had drawn it before did not satisfy the right hand rule. So A cross B, you follows the right hand rule. In this case, the way I drew it, A cross B would be pointing up. I'm going to give you a shortcut here. Now, you may see this as a shortcut, or maybe you just like using the formula. And then I actually might change up the numerical example to do maybe a new one. So the visual trick is this. If you have your two vectors A and B, you write them out vertically like this. You actually start with A2, and you do A2, A3, back to A1, and write A2 again. And you do the same thing with B2. You start with the Y value. B2, B3, B1, and then write B2 again. And then the three values for your cross product come from doing a little cross multiplication. The x value comes from doing this cross one. You do A2, B3 minus A3, B2. And this is just the same formula. This is just a visual way of remembering the formula. To get the y value, you do the top left to bottom right, A3, B1 minus A1, B3. And then finally, A1, B2 for Z minus A2, B1. Now, we've actually shown this works. We've used the formula already for this guy. So let's do a new one. So let's do 2, -1, 3, and 5, 0, -4. Why not? So here's how this works. So we're finding the cross product of these two vectors A and B, a vector that's perpendicular to both. Let's rewrite vector A. Start with the y value, -1, 3, 2, finish with the y value again, and then do the same with the second vector, 0, -4, 5, 0. To get your x value, and some of you guys might not have to show a lot of work for this. Some of you guys, you can show more work if you like. But to get the x value, we do this. So it's got 4 minus 0, which is 4. For the y value, 15 minus -8. So I do write down this little intermediate step just to so I don't make a mistake with signs, 23. And then 0 minus -5. It gives me 5. So the cross product of these two vectors is 4, 23, 5. But I'm sure that some of you guys, after writing out this little vertical array, could have just gone right to your answer. And that's it. Can you guys try this one? Try using our trick. Oh, I suppose that those both can't be vector v or u, so we'll make that one vector v. So can you guys try u cross v? If you want to pause the video and unpause when you're ready, you can do that. Or you can follow along with me right now. So we write out vector u, 5, 0, 3, end on 5 again. We'll write out vector v, 4, 0, -3, 4. You love to see those zeros. Makes it a lot easier because we get 0 minus 0. And then for the y value, 0 minus 0. And for the z value, we get 12 minus -15 equals 27. So in this case, u cross v is the vector 0, 0, 27. And if I may, this actually makes a lot of sense. We have some experience now visualizing vectors in R3. And 350 and -340 are vectors that lie in the xy plane, right? Because 350 would be something like out here, I think. -340 might be something out here. But both of those vectors lie in the xy plane. So it makes sense that a vector perpendicular to both sticks directly out of the xy plane, is parallel to the z-axis, and that's what you get, 0, 0, 27. So our answer makes sense. Let's do one more, give it a try, and then I'm going to show you guys how we can check our answer using the dot product. So again, if you'd like, you can pause the video and unpause when you're ready, or follow along with me. But it is nice to know that we can check our answers. So uv 4, 7, -2, 4, x value -35 plus 4, or subtract should be -35, minus -4. Got to be careful of the negatives floating around. This is -31. I think it's right, but I mean, I'm going to check in a second, so I won't worry too much about it. 2 minus 21 is -19. And 12 subtract 10 is 2. So I think that I did it again, u cross v. I think U cross V is -31, -19, and 2. Well, we can check our answer using the dot product. Oh my goodness, there's so much going on with this question that's wrong. I said U and U, and then said do the cross product A and B. So let's use U and V, and just this should be U cross V. Sorry about that, guys. Not a big deal. So let's check it out. So let's do this vector U cross V. It should be perpendicular to both. So if I do 3, 5, -1 dotted with -31, -19, 2, does this equal 0? Well, let's find out. That is -93. Or right away I can see that I did something wrong because I'm not getting 0. That's okay though. Let's go back and find my mistake. So -5, -1, 3, -5, 4, 7, -2, 4, -35 plus 4, that's okay. 2 take away 21, that's okay. And, oh, I know what my mistake, I don't think my mistake was in the cross product. My mistake is a copying error. It's -5. Because then I'm going to be adding 95 and then subtracting 2, and it gives me 0. All right, so it looks like we did okay. But let's check the second vector too. -2, 4, 7, dotted with our cross product, -19, 2, gives me 62. 4 times -19, minus 76, and 7 times 2 is 14. And yeah, those total up to 0. So it looks like we did a good job there. So if you're doing, this doesn't need to be done all the time, but if you're doing an evaluation and you want to make sure if you have the time and want to check your answer, then you can. All right, there's a key idea here though. The vectors A, B, and A cross B are related to be the dot product because A cross B is perpendicular to both vector A dotted with the vector A cross B gives you 0 all the time. And the same with B. B dotted with A cross B equals 0. And that's true for all vectors A and B. So we're just turning that check we did into this general idea. It works all the time. So what's interesting about the product is, so all your math careers from right now, you guys have been thinking of product, multiplication, it's commutative. 2 times 3 is the same as 3 times 2. And then recently, A dotted with B was the same as B dotted with A. Does A cross B equal B cross A? We're actually going to show that it doesn't, which is kind of cool. So what does B cross A equal to? Let's use the formula. And we're just going to be switching the values of A and B around. So this time, instead of A2, B3 minus A3, B2, I'm going to switch the values around. So it's B2, A3 minus B3, A2. And literally what we've done is we've taken the formula that we did earlier, and just every B and A, we just swapped places. And then we'll have B3A1 minus B1A3 and B1, B2, B1A2 minus B2A1. Now, just with a little bit of manipulation here, if I took out a negative from all of these guys, I would just switch the order of the subtractions here. So I would get B3A2 minus B2A3. So just switching the orders of each one of these guys, and then I get B1A3 minus B3A1 and B2A1 minus B1A2. Now, I have mentioned that the cross product isn't commutative, but inside these calculations, these are numbers. Like the order of multiplying two numbers doesn't matter. So if I flip-flopped every single one of these 6 multiplications, A2, B3, A3, B2. I can, because those are just multiplying numbers together. A3, B1, A1, B3, and A1, B2, A2, B1. That is the very definition of A cross B. But what we have out front is this negative sign. So this is super cool, actually. B cross A is the negative of A cross B. They're opposites. And we've proven that just by using the formula for the cross product. Now, I want to go way back to this visual here, and I want to add one more thing to it. A cross B, using the right-hand rule, in that particular diagram, gives you a vector that points straight up. B cross A in this diagram would give you a vector that points straight down in this diagram, and it would be opposite to A cross B. So can you add that vector in as well? And this makes sense. Like for me, I'm putting my hand out, my arm, like it's vector B, and I'm curling it down towards A, and my thumb at home here is pointing towards the floor, down. So that's kind of cool. So this is your first example of a product that does not obey the commutative property. The cross product does obey a distributive property, though. And in this one, we won't do a proof. We'll just state the property, and then you can just use it. So vector A crossed with some vector addition, B plus C. That's the same as if you did A cross B plus A crossed with C. And that's true for all vectors A, B, and C. But we're not going to prove that one. That one we can just feel free to use whenever we need it. All right. So far, what you guys should be able to do, well, one is understand what the cross product gives you. It gives you two vectors that are perpendicular. It gives you a vector that is perpendicular to your two vectors in the product. You should know how to calculate it, and you should understand the right-hand rule in that A cross B and B cross A are not the same. In fact, they're opposites. I'm going to show you guys now. The last thing we'll do is a cool application of the cross product. It has to do with parallelograms in their area. And this is especially useful for R3 and when we get to like 3D modeling, if you get into that kind of thing. This can be very useful. So just for now, consider this parallelogram formed by two vectors that are tail to tail. Now, the area of a parallelogram is, I'm sure you guys all remember from grade 9, is base times the height. And in this particular diagram, the base is represented by the length of vector u. And that height, using trigonometry, a little SOHCAHTOA, would be because that height is opposite the angle theta there, the angle between the two vectors. You would use sine, and you would get that height is equal to the length of the hypotenuse, which is v, times sine theta. So the area of that parallelogram, if you knew the vectors u and v, you could find, if you could find the angle between them, you could calculate the area. And in fact, we're going to do that, and we're just going to make up. Now, you can feel free to use your own vectors at home, or you can use the ones I'm going to do. I'm just going to choose some nice simple numbers. So just 1, 2, 3, 4, 5, 6. Let's find the area formed by these two vectors. So I've told you guys how to do that. Magnitude of u, magnitude of v, sine theta. That's just from like just simple grade 9 and 10 math. We can find the length of u, find the length of v, find the angle. We can get the area. And we've developed tools for us to find all those three things. So I might just be compact and just to save some space. Not sure how much space I'll need. The size of u is the root of 1 squared plus 2 squared plus 3 squared, which is 10 with the root of 14. I'll leave it like that for now. The root of v is the root of 4 squared plus 5 squared plus 6 squared. I'm going to use a calculator. I've messed up too many times today. Plus 25 plus 36, root of 77. To get the angle, we're going to use a dot product. Because remember, we know that the cosine of the angle is equal to u dot v over the size of u size of v. And u dot v is equal to, so that'd be 4 plus 10 plus 18 over the two magnitudes. So I'm shaving off a bit of work here. It's assumed you guys have been, practicing and, found lots of angles between vectors. Plus 18. So on top, 32 divided by the root of 14 and divided by the root of 77. That's an awful 77. So I got about 0.9746, and the angle between them, shift cosine, about 12.9. I'm going to keep a tiny bit more accuracy here than I normally might. I'm going to say 12.93. All right. Now, so we've got those three things. Let's find the area. So for part A, our area, it was going to be size of u times size of v times sine theta. So that is root 14 times root 77 times the sine of 12.93 degrees. Let's see what that gets us. Sine times root 14 times root 77. So I got about 7.35. And that would just be square units here. You might be wondering, what's the connection with the cross product? Well, now you guys are going to see. Can you guys find the cross product? One more cross product for you guys to find. So let's lay out our vectors: 2, 3, 1, 2. And 5, 6, 4, 5. 12 minus 15 is -3. 12 minus 6 is 6. 5 minus 8 is -3. So here, u cross v is equal to -3, 6, -3. And the size of that vector would be the root of -3 squared plus 6 squared plus -3 squared. And let's see what that gives us. I hope it works out. Plus 18, get the root of 54. And if you evaluate the root of 54, so that's the exact magnitude of the cross product. But if you evaluate that, you do get 7.35 units. So this is really cool. There's actually this connection between areas of parallelograms, and it doesn't matter whether it's, well, it does matter. It has to be in 3 space because you can't do cross product in R2. The area between any two vectors in R3 is equal to the size of the cross product between those two vectors. So 2 key ideas for you here. One is what we just showed, the area of the parallelogram formed between 2 vectors say u and v is just the magnitude of the cross product between them. You don't have to do a lot of hard work in visualizing and draw those vectors in 3D and then find the base and height. No, you can just find their cross product and find its magnitude. So that wasn't quite a rigorous proof we did, but yeah, hopefully you're convinced that it works. The second thing can be useful too, is that in terms of geometric vectors, we actually have a way of calculating the size of the cross product, and it's equal to the size of u times the size of v times sine theta. So those are the 2 big takeaways from that problem there. I should say too, if you you could also use this idea to find areas of triangles, right? So let's say you wanted to find the area of a triangle between formed by 3 points in R3. You could use the cross product, because you could calculate the vector A, you could calculate what the vector AB is, calculate what the vector AC is, find the area of the parallelogram formed between the two of them by doing A cross B, AB cross with BC with AC, and then find half of that, because a triangle is half a parallelogram. So you could find the size of AB crossed with AC, and then divide that by 2. So that gives you the area of a triangle formed by 3 points ABC. So a lot of interesting things you can do with that. And there's a lot of physics applications that involve cross products as well. Specifically, 2 specific ones would be torque, which we'll see in a bit. But if you've taken physics, you might have worked with electromagnetic fields, and you understand that electric fields and magnetic fields are kind of related perpendicularly. That's a really vague and loose definition. But the cross product shows up a lot in the math behind electromagnetism. Okay, that's enough for today. I've given you guys some practice here to try. And the last thing we'll do is some applications of the cross product and dot product before we finish up this unit. So try the practice. Let me know if you need anything. Hope you guys are doing well. We'll see you soon.